In this section, 13.4, we're going to look at two fluid flow equations. The first of these fluid flow equations is going to be equivalent to the conservation of mass, or otherwise known as the equation of continuity. The other equation, the same, will be equivalent to the conservation of energy, and it is often called Bernoulli's equation. So let's see how these equations arise, because we're certainly familiar with both the conservation of mass and the conservation of energy. And these two equations show how that is demonstrated mathematically in the form of an equation when we're dealing with a fluid. Let's first of all look at the equation of continuity. It states that the mass flow rate at two different points in a fluid are the same. That's equivalent to the conservation of mass, and let's look at it explicitly and mathematically. The equation of continuity says that the density at one point in the fluid, and here we can imagine we've got two places, a point 1 and a point 2, and we look at the density 1 times the area 1 times the volume at point 1, and that will be the density at point 2, the area at point 2, times the volume at point 2. So that's density times area times volume. And by area, we of course mean the area of these cross sections, which can be different. Now, how does this relate to the conservation of mass? Well, let me rewrite this, and rather than derive it directly, I'm going to rederive the conservation of mass from this to say that the mass at this point is the same as the mass at this point per unit time. So I'm going to take rho 1 and say, well, rho 1 and rho 2 are about the same. So let's take that particular case where they're the same. And so I'm going to call rho 1 and rho 2 both rho. And now the area times the velocity, I'm going to write the velocity is dx over dt. So here's an area 2, it's area 1, times dx, this is dx1, this is dx2 over dt. Now that's the velocity of the fluid, how far it travels, dx1, and how far it travels over here, dx2. With a given area, A1, given area here, A2. And for the moment, I'm going to take the density to be the same in both cases. Now, the area times the distance will give me the volume. So this is the volume 1, and this is the volume 2. Now, we have the density times the volume 1, and here the density times the volume 2. So this equation becomes the mass at point 1 that's contained here, that's moved, divided by dt, is equal to the mass, density times volume, which would be the mass at point 2. And therefore, the mass at point 2 that's changing is the same as the mass at point 1. Therefore, mass is conserved, or the mass difference if I were to move it over here. Now, as far as these densities go, if the densities were to vary here and here, we would still get the mass by taking the first density times the volume here, and the second density times the volume here. And so you can see that even though the rows are different, so I have rho 1 and rho 2 for two different densities, still it's going to give the conservation of mass. So this one is called the equation of continuity. The equation of continuity. And it's the same as the conservation of mass. In other words, the mass of the fluid at one place is going to be the mass of the fluid at another. Let's see if we can look at that intuitively. Let's imagine we have a hose pipe. What we want to do is wash the car, so we narrow this down to where this is a very, very small opening. This is a nozzle. And now, as you can see, the water is going to come at one rate here, but it's going to go extremely rapid right there. Why? Because the volume of water that comes forward here has to go out the end, or else it would just build up here with greater and greater pressure. Therefore, it has to go out with a very, very high velocity, since this restriction is very small. In other words, by restricting the area to be small with constant density, the velocity must increase. Therefore, a good test question is, is if this area is 1/10 of this area here, how fast must this go out? Well, if this area is 1/10 of this, so this is 1/10 of A1, this must be 10 times V1. Therefore, the velocity here must be 10 times as great. A simple proportionality. And in those cases, we just assume the two rows are the same. It's the equation of continuity, conservation of mass, and we've worked a problem there. Okay? Now I want to look at this other equation. This is called Bernoulli's equation. Bernoulli lived from 1700 to 1782. He's a very famous physicist and had many results, but this is one of his most famous in his study of fluids. And this equation governs the steady or non-viscous incompressible fluid flow. Let's go over that again. It has to be steady flow, has to be non-viscous, and has to be incompressible. So if you start using gases, this is not going to work. What is the equation equivalent to or derived from? The answer is the conservation of energy. And we're going to begin with the equation, which looks pretty messy, and do again an inverse solution. So we're going to write here, section 13.4, fluid flow equations. We're going to write P1 plus 1/2 rho V1 squared plus rho times G times Y1 is equal to pressure at a second point plus 1/2 rho V2 squared plus rho G Y2. Now if I were to draw a diagram that would be appropriate to this, then what I would be drawing would be something like a fluid that went through some altitude change, height Y1, height Y2, and it had a velocity here, V1, and a velocity here, V2. It had a pressure here, P1, and a pressure here, P2, as it flowed through some type of pipe. Now the way that I'm going to do this is an inverse solution also. I'm going to take this pressure and write the pressure by saying, well, pressure is the force per unit area. And since pressure is the force per unit area, I can multiply both of these by a distance x through which this goes. The same would be over here. I'm going to take this density and write it as a mass divided by a volume. And I'm going to do the same thing here and write this density as a volume times a density divided by a volume. And when I did that, I just multiplied by volume and divided by a volume times G times Y1. And of course here, I just wrote the density as a mass divided by a volume. I could do the same thing over here, which I'll do in a moment. Now you'll notice this area times the distance. This is going to be the volume here. And the force times the distance that the fluid moves is going to be the work. So this is going to be the work. And I have a volume dividing this, and dividing this that will cancel. And likewise on this side of the equation. So work plus 1/2 mv squared. Well, we know what that is. That's the kinetic energy at point 1, the work that's done at point 1, plus, the volume here is canceled. Here we have rho times v, well that's the mass, so this is mg times the height here, so this is going to be mgh1. And so we see this as the work done plus the kinetic energy plus the potential energy, and that's the total energy, is going to be the same thing as point 2. So this is going to be equal to the work 2 plus kinetic energy 2 plus mgh 2, or equivalently potential energy 2. So we have the total energy at point 1 is equal to the total energy at point 2, and therefore this Bernoulli's equation is the equation that relates to the conservation of energy. Now when we're looking at a pipe that goes through different altitudes, therefore, we have to be able to look at the difference in the height. The h1 minus the h2 times mg, or here, rho times g, if we bring the y2 over to here. And so we can look at the change in potential energy, change in kinetic energy, because it might move at a different velocity, and the difference in the pressure. So this right here is our critical equation, but you can see it's only one factor away from being the conservation of energy.